When we have an alternating series, we can further characterize its convergence into absolutely convergent and conditional convergent. Let's start with the definition. If we have a series sum of an, which is an alternating series, then the series is called absolutely convergent if the series of the absolute values, so sum of absolute of an, is convergent. The sum of absolute of an, which also means we have the sum of the absolute of the terms, that is absolute of a1 plus absolute of a2 plus absolute of a3, and so on. And the series sum of an is called conditionally convergent if it is convergent but not absolutely convergent. In other words, sum of an converges but not the sum of absolute of an. And the theorem says if a series sum of an is absolutely convergent, then the series is convergent. So if we have an alternating series that cannot be proven is convergent using the alternating series, as long as we can prove that the sum of absolute of an is convergent, which also means the series is absolutely convergent, then we can use this theorem. If the series is absolutely convergent, then the alternating series is convergent. Let's look at the first example. We want to determine whether the series sum of -1 to the power of n minus 1 divided by n squared is absolutely convergent, conditional convergent, or divergent. Let's first write out the first few terms. The original series, sum for n starting from 1 of -1 to the power of n minus 1 divided by n squared. The n starts from 1, so the first term, the exponent is 1 minus 1, which is an even number. So it will start from positive. So 1 minus 1 over 2 squared plus 1 over 3 squared, then minus 1 over 4 squared, and so on. And we can see that this series is convergent by the alternating series, because the bn plus 1 is always smaller than or equals to bn, and the limit of bn as n approaches to infinity is 0. How about the series with absolute of the terms? So the sum for n starting from 1 of the absolute of -1 to the power of n minus 1 divided by n squared, which also equals to the sum for n starting from 1 of 1 over n squared. The first few terms are 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. And this is a series that we know. This is a p series with p equals to 2. So it is a convergent p series. So the series of absolute of an is convergent. So the series is absolutely convergent. How about this series? The sum of -1 to the power of n minus 1 divided by n. Is this series absolutely convergent, conditionally convergent, or divergent? This is an alternating harmonic series. If we already look at this example in lecture 20, we found that the alternating harmonic series is convergent. How about the series with absolute of an? We can see that absolute of an is 1 over n, which is a p series with p equals to 1. Since p equals to 1, so the series of absolute of an is divergent. We have the series of absolute of an is divergent, but the alternating series is convergent. So this series is conditionally convergent. Now let's look at the last example for this lecture. Is the following series absolutely convergent, conditionally convergent, or divergent? the series is sum of cosine of n divided by n squared. Since a cosine function also alternates between positive and negative, so this is also an alternating series. However, it is not that obvious that this series satisfies the two conditions for the alternating test. So instead, we could investigate the series with absolute of an. So the sum for n starting from 1 of absolute of cosine of n divided by n squared. The n squared is always positive, so this also equals to the sum of absolute of cosine of n divided by n squared. And we know that a cosine function oscillates between -1 and 1. So absolute of cosine function is always smaller than or equals to 1. So this is smaller than or equals to the series, the sum of 1 over n squared. And this series is a p-series with p equals to 2. So the series of absolute of an is smaller than a convergent series, which means that by the comparison test, the series for absolute of an is convergent. Then, we can use theorem 3. If a series is absolutely convergent, then the alternating series is also convergent. So this is an example where we don't have to use the alternating test. Instead, we investigate the series with absolute of an. And we can show that the series with absolute of an is convergent, which means the series is absolutely convergent. Then using the theorem, if a series is absolutely convergent, then the alternating series is also convergent. And that is the end of the lecture. In the next lecture, let's look at the 6th convergence test, the ratio test.